Let's find the general solution to a second order homogeneous recurrence relation with constant coefficients. And to do that, we'll use our solution that we derived for the first order recurrence relation as a guide. So this was the constant a by negative c1 to the power n. So therefore for our second order recurrence relation, we assume a solution of the form Sn is lambda to the power n. And now we can substitute this in our recurrence relation. So what we get is lambda to the n plus the constant by lambda to the n minus 1, and then plus our other constant by lambda to the n minus 2. And that's equal to 0. And now we can factor out lambda to the n minus 2. So what we have is lambda squared for the first term. So lambda to the n minus 2 plus 2 is lambda to the n. And for our second term, we have c1 lambda and then plus c2. And that's equal to 0. And therefore for an arbitrary lambda, this equation here must be 0 to satisfy this equation. And this is known as the characteristic equation. And we can see it's a quadratic, so the solution is obtained using the quadratic formula. So that would be minus c1 plus or minus the square root of c1 squared minus 4 by 1 by c2. And that's divided by 2 by 1, which is 2. And this term here is the discriminant, which we'll call d. Now there are 3 cases that can be obtained, and one of those is where the discriminant is greater than 0, where we get 2 distinct real roots. And these roots are lambda 1 is minus c1 plus the square root of the discriminant on 2, and the second root is the negative root. So we have minus c1 minus root d on 2. And recalling that our assumed solution was Sn is lambda to the n, and we had a second order recurrence relation, which means we require 2 initial conditions. So our solution Sn is a superposition of 2 solutions of this form. So it's a constant by lambda 1 to the n plus another constant by lambda 2 to the n. Now for our second case, the discriminant is equal to 0. So here you would get a repeated real root. And that would be lambda is equal to minus c1 on 2. So therefore in this case our solution would be a constant a plus a constant b multiplied by n by lambda to the n. And here we superimpose 2 solutions of this form, where the second one is multiplied by n, because otherwise you'd have a constant by lambda to the n and you'd only need 1 initial condition. So this is the correct form of the solution for this case. And the third case is where the discriminant was less than 0 and you'd get 2 distinct complex roots. So as we can see, if d is less than 0, then what you'd get is a complex number. You have minus c1 plus the complex number I root d on 2. And similarly The second root will be minus c1 minus I root d on 2. And we can ignore this third case because we'll be solving recurrence relations that give real solutions. Please subscribe, like and comment to help me reach more students.